Hello, folks. This is Dr. Stephen LaBeouf of Valencell. Thanks for your time today. The presentation today is called What Can You Do with a Heart Rate Sensor? And I guess what spawned this presentation and this concept is that when people think of heart rate monitoring, they might think of heart rate only, or they might think of heart rate zones, and they may not know some of the things you can do with heart rate itself, but also even broader than that, what you can do with a PPG, or rather, more focused than that, rather, what can you do with a PPG-based heart rate sensor that you may not be aware that you can do? We, at Valencell, we work with a lot of different companies to help them figure out novel ways of employing our technology, and then also even sometimes very well-known methods of employing our technology in ways that are interesting and compelling for really exciting use cases. Things that keep consumers engaged, or that keep even end users in any particular way, depending on the application, engaged with what they do. And it turns out there's a lot more inside of a heart rate monitor, in particular a PPG-based heart rate monitor, than most people are even using. So we wanted to share with you the types of things you can do that you may not be aware of, and then open it up to questions for you all after the presentation. So, this plot here, this blue plot here, is a plot of a PPG waveform. It actually is an inverse plot. So it's an inverse plot that comes out of a sensor. And I believe this PPG data is actually mine. Actually, my own PPG data from a breathing control session I had. And if you look at this PPG data, there are a number of different pulses in here. I just eyeballing it right here, maybe about 40-something or so pulses inside of this PPG waveform. And if you look at the time between the different peaks, that's how you can understand heart rate. And if you look at finer resolution between the peaks, you can pull out the RR interval, the time between the individual peaks within milliseconds of resolution. If you look at the amplitude of each peak, it gives you the peak amplitude of the PPG wave, and that's indicative of the pulse pressure of the person. If you look at the longer frequency changes here that happen between this kind of envelope function here between these peaks, that's indicative of your breathing rate. And then if you look at these sweeping kind of DC level changes here, that's indicative of your perfusion variation, how that's changing over time. And it turns out that if you appropriately analyze a PPG waveform, you can pull out not only heart rate, but breathing rate, heart rate variability, and that's done by doing statistics on the time between the individual heartbeats. And there are many established ways to do that, and then some that are proprietary that are also very interesting. We'll talk about both today. Also, cardiovascular fitness can be determined from a PPG wave analysis, and this can be in terms of, for example, a VO2 max estimation, or a cardiac efficiency estimation that comes from looking at how many heartbeats it takes for you to move a footstep. Also, you can get an assessment of your blood pressure and your blood oxygenation. Now, the blood oxygenation typically requires, for that type of assessment, you typically require multiple wavelengths, at least two wavelengths that are far enough apart where you can look at the different absorption profiles of hemoglobin. But frankly, you can do a blood oxygenation estimation even with one wavelength. And we've even been able to do that in our labs. Of course, it's not nearly as precise as two wavelengths, but you could find out, for example, if somebody is in a real dire strait, needs oxygen or not from that analysis. And also, another thing you can pull off is the blood perfusion, which is in particular how well blood is flowing through your skin. Now, when you look at all these different outputs here, if you look at heart rate itself in context of activity, and also RR interval, or the heart rate variability in context of activity, there are a number of different types of analysis you can pull off. And what I did is I put together this chart for you so you can see the types of things, the types of assessments you can pull off of heart rate and RR interval information in activity information such as cadence alone. So everything I have listed here are things you can do with the outputs of Valencell's technology that you can get in a benchmark sensor, for example. And some folks, some of our customers have implemented these types of things already. Others have not. And some of these people haven't even implemented at all yet. Different companies have not even implemented these at all yet with our technology at least. And I'll go through these with you. The first one is VO2 max, and that's your aerobic capacity. It's basically how much fuel can you use for activity. And it's a good marker for your overall cardiovascular fitness. You know, when VO2 max was first utilized, historically, I believe it was used as a gauge for mortality because it's strongly correlated with how well you will recover from, say, a cardiac event. Over time, I believe it got more used for athletic performance monitoring, and now it's used both medically as a way in recovery for cardiac events, and then also is used as a marker for your athletic performance, how well will you perform in any cardiovascular activity. And note on the right here, I have what it means for health. I've got these different references. You can click on them and go to those references, and it shows you how you can use, first of all, how you can generate a VO2 max assessment using heart rate and cadence, but also additionally how you can use it. Then there's resting heart rate, which is more common to most people. Most people understand what resting heart rate is. It's technically defined as your heart rate during an awake period with no exertion. And that's important because you cannot get your resting heart rate while you're sleeping because you're not awake. That is not your resting heart rate. Your resting heart rate is your heart rate where you're awake with no exertion at all for a period of time. That's why one of the ways it's encouraged for you to measure your resting heart rate is right after you get up with no alarm going off. If an alarm gets you up, it destroys the resting heart rate measurement, and you're in the awake state. But there are other ways to do this depending on the time of day when you measure your heart rate. You can do an assessment to estimate your true resting heart rate based off your circadian rhythm and what that is. And what's known is that if your resting heart rate decreases, that's improved fitness. Decreasing resting heart rate is correlated with increasing fitness and actually reduced mortality, so you live longer. And that's well documented. It's actually documented across not just humans, but even animals. And one of the things is that there are several studies that show that a steadily increasing resting heart rate is correlated with the progression of cardiovascular disease. And I put several references here for you to take a look at. Heart rate recovery also is actually being used by a lot of our customers right now. Typically, that's defined as how your heart rate changes over the course of a minute after intense exercise. And one of the things about heart rate recovery that's interesting is it gives more insight into how well you can perform during an endurance exercise. It's an indicator of your endurance, and it's a closer indicator of your endurance than, say, VO2 max and resting heart rate in many cases. And it also implies better cardiovascular health. There's plenty of papers on this. Now, the one below it is pretty interesting. Most people don't think about this in the sports and fitness world. It turns out to be really important in the medical world. It's your heart rate response. And it's how your heart rate changes over the course of, say, a minute. And what's interesting is if you are suffering from a cardiac condition, you can have a situation called chronotropic incompetence. And what that means is when you go from, say, rest to an activity, your heart rate will change extremely rapidly and then flatten out. And the reason is because your heart rate dynamics are all screwed up. Your heart rate can't catch up to your activity. And so you see this really hard swing in your heart rate response followed by flattening out. And that's indicative of a really big problem. That's actually you see that in a heart rate monitor, that's a really big red flag. If the person doesn't have, say, chronotropic incompetence, it could be that they are, you won't see that, but you might see that the heart rate response is very, very pronounced. And that could simply mean, without the flattening out, and that could just simply mean that they're not ready for exercise. But if you see that sharp rise and they're flattening out there, that's a red flag. Cardiac efficiency is a metric that Valencell encourages our partners to use. It looks at basically the fitter you are, the less work it takes, the less heartbeats it takes to move a footstep. And so what's cool about cardiac efficiency is it's a strong correlator for your health. It can also let you know if you're becoming hypertensive, but also it's easy to implement. You can look at a whole data set of heart rate and cadence information taken over a period of time and easily process that data set and give someone a health assessment right away without even factoring what they're doing, because their heart rate is normalized in part by the cadence measurement. So when you ratio the cadence divided by the heart rate and the average of those, you get a really interesting trend that's very easy to process in wearable devices. And then the last one here, heart rate variability, is one that has a lot of mystery behind it, I guess. But really, the reality is it's just simply statistics done on the RR intervals. And with heart rate variability, you can diagnose a number of different things, both psychosocial stress, overtraining, exercise. You can even use heart rate variability to predict atrial fib or arrhythmia by processing the data signals. And in Valencell's labs, we've done this. We've done it accidentally. We've had participants come to our labs and take RR interval testing with either our wrist-worn wearable prototypes or our ear-worn wearable prototypes. And on the left is a normal Poincare plot. Now, the Poincare plot just takes one RR interval and plots it against the next one and just keeps doing that. So you have the first RR interval or the first time between the first two heartbeats, you plot that versus the next time between the next two heartbeats. And in a normal plot, you get this nice, I guess, for lack of a better term, football-shaped type distribution. And the narrower that is, typically, and the longer it is, typically the fitter people are, and also oftentimes the less stressed they are too. But when someone has atrial fib, it breaks out because your heart jumps between these different modes in a way, and you see this kind of cross-like pattern or cloverleaf pattern, I've also heard it called. And we've seen this at least 3 times in our laboratories. In one case, the person had chronic atrial fib and knew about it. The other 2, they didn't know. And as a matter of fact, subsequent testing, we couldn't always find it because you don't always necessarily have atrial fib going on in you if you have the condition. That's why it's considered one of the silent killers. But literally, y'all, this plot was put together simply using Poincare analysis. There was no special processing, no proprietary processing on the RR interval outputs. You can do this and do this own assessment with our existing RRI output from our benchmark sensors. And there's a lot more you can measure and assess with heart rate. What we did here is present to you kind of a summary of the different types of things you can pull off of a PPG heart rate sensor here, especially with activity context. For example, you may not, if you look at the right-hand side, a lot of folks don't know that you can estimate your core body temperature during exercise with a heart rate monitor. And we're going to show you how that's done. And I also am going to show you a reference you can check, and you can just pull up the reference and you can implement it. If you want help from Valencell, we can show you how to do this. It's part of our standard, what we offer folks if they get a benchmark sensor, we show them how to implement this. But you can estimate core body temperature during an exercise with the heart rate information only. And it's pretty useful, especially for overheating use cases and concerns there. Also, energy expenditure, your calories burned. Adding heart rate into your energy expenditure model will improve your accuracy. You can also get an assessment of hydration, stress, and a variety of other parameters here. And I'm going to talk about a few of these. In particular, I'm going to talk about, for example, core body temperature. I'm going to talk about energy balance. I'll talk about sleep and stress. So let's talk about core body temperature. Now, there was a study that was led by Dr. Bulla at Brown University Computer Science Group, and also Therian of the Army Research Institute of Environmental Medicine. What they did is they took a number of participants and they tracked how their heart rate changed in time dynamically with exercise compared to core body temperature. And you probably don't want to know how they did their benchmarking for the body temperature, but I'll just say it's not the way I'd like my body temperature measured. And during this study, they were able to see using a Kalman filter on the heart rate, K-A-L, my accent may kind of distort it, but it's K-A-L-M-A-N, Kalman filter. They applied a Kalman filter to the heart rate data, and they wrote a paper on how to do this. And I have a link to the paper here. If you're interested in this, I highly advise you to check it out. We can also help you further here at Valencell because we've implemented it in our SDK. And it's based off these time-oriented changes in heart rate during exercise. And by memory, don't quote me on this, by memory now, the accuracy was on average about 0.3 degrees Celsius. So that was the mean error, plus or minus 0.13 or 0.13 degrees Celsius, give or take. And I remember that also in its paper, they were able to get within 0.5 degrees Celsius, something like 80 or 85 or maybe higher percentage of the time. So a large percentage of the time, they maintain that accuracy in the data set. So you can really use this to gauge overheating, which is what they were concerned about, because this was an Army-funded study, or at least Army collaboration study on trying to prevent overheating. And, there's another way you can do this as well, and you can improve the accuracy of the core body temperature estimation if you employ activity context as well. You can see when the run starts and when it stops. I don't know if y'all can see that the heart rate plot has the diamonds in it, and then the cadence plot is just a line. And the person here in this case is running at a steady cadence when they start the run, and the heart rate is steadily increasing. And that's typical of the overheating scenario. And when you combine that with the last reference, with the activity context, you can further improve your estimation as to whether or not somebody is overheating or not. Now notice at the bottom, there's an average heart rate divided by average cadence there. The inverse of that is the cardiac efficiency. So we often look at this to get an indication of how fit the person is. For example, that's the inverse of the cardiac efficiency. So the higher that is, the less fit they are. So let's talk about energy balance. Now, energy balance is a balance of the energy you take in versus the energy you take out. So how much you're grubbing up versus how much you're burning. And in this field of energy balance has really started to take off in the last decade. One of the more recent pioneers in this field is one of our collaborators, Dr. Krause, at the Duke Center for Living in Durham. And I put a link here to a presentation he gives on energy balance. And I got to say, I misspelled prevention, I see here, so please pardon that. But that was my fault. But if you click on that link, you'll get to a presentation where he goes over what is understood about energy balance versus health. Now, it turns out that if you employ, say, a branch equation model where you put in your activity information and the heart rate information, you can greatly improve your accuracy for energy expenditure. And that's important because if you want to stay within energy balance, you want to burn what you consume. And one of the things Krause talks about in this paper is the slide deck rather, is he talks about how if you stay within energy balance, your triglycerides improve, your cholesterol improves substantially. And this, by the way, this work that he did, your blood pressure improves. This work that he did was based on the STRIDE cohort, which is funded by the NIH. So this was, several hundred people in this study. So it's well documented. It's very useful. The challenge is, there's two challenges right now with energy balance in wearables. One of them is there's no good way to see what people have really eaten. You're taking their word for it. And there's no good way to really monitor the calories consumed or eaten by a person. So you do kind of the best you can. So, a lot of research has been focused on what you can measure, which is their energy expenditure. But even then, it's not as good as it needs to be for clinical utility. For example, if your energy balance is off by about just 3%, you can become obese within a year. So if your energy balance estimation is off by, say 5%, if your error for calories burned is 5%, you're not really helping somebody from a clinical standpoint. You can help them from promoting and guiding them, don't get me wrong. But as far as a clinical use of energy balance, you can't really help them like you need to. And nobody's there yet. We're not there yet. Valencell, and nobody has been able to get there yet. But presumably with sensor fusion, we ultimately may be able to get there. So let's talk now about sleep and sleep-oriented disease and how you would do that with a heart rate monitor. I put here several links here. All of these links show you how to use a heart rate monitor to gauge various aspects of sleep. So, I know a lot of you are very, very familiar with sleep, so I won't ad nauseum you about that, about the different stages of sleep, and about wakefulness versus deep sleep versus REM. The things I think that are really interesting to point out here is how you use heart rate for those cases. So, for example, I put a link here for how you would use heart rate and a heart rate sensor to estimate sleep apnea, or to know that that's happening. There's Dr. Thomas Pinzel in Germany, the Philipps University, has produced a few papers on this. I put a link to one I thought was particularly important for you all to take a look at. And what he shows and what he finds is that you can tell if somebody is suffering from sleep apnea by a low percentage of deep sleep as determined by a low percentage of low heart rate steps. So when you look at someone's sleep data, if they are able to go into a deep sleep, you see these dives in their heart rate. And if you don't see them, they could be suffering from sleep apnea. And he shows how to do that. So you can look at sleep data and look for these drops in heart rate. Now, you'll need high enough resolution on the heart rate to catch those drops. But if you have an accurate heart rate monitor, you'll catch them. And it'll help you with a diagnosis of whether or not someone may have a screening for sleep apnea. And that's done with heart rate alone. Also, you can detect disruptions in breathing, which could be caused by a number of things. Maybe not sleep apnea. It could be, various types of arousals. And I've got a link for you there. Karmakar and all have a paper on this. Their paper is interesting. They detect disruptions in breathing based off of three characteristics of a PPG heart rate monitor. One is the heart rate itself, or the time between, the heartbeat, the time between each beat of the heart. Also, they look at the amplitude, the PPG amplitude of the pulses. And I'll show you some of that stuff in a bit, how that works. I'll show you some of our own data on that. And then also, they look at the area under the curve of a PPG peak. So, if you go back to that slide 2 where I showed you my PPG waveform, the area under that curve, they also put into the model. So they factor the heart rate, they factor the PPG amplitude, and they factor the area under that curve. They found that they can detect these disruptions in breathing. They can characterize them. They can tell when you actually are up, when you're awake and not. So that's pretty interesting. That uses, again, only a PPG sensor. For heart rate, it doesn't require any other input. Another one is detecting, differentiating between sleep stages. And those sleep stages there's a classification methodology you can use for that, based off only a PPG sensor. And the accuracy of those, I've seen the classification rates. I believe there's a classification rate that's something like 85%, 87% classification. Then also you can determine sleep versus wake stages and categorize those. Okay, am I up or am I really sleeping? And there's a paper by Lewicki et al. That explains how to do that with heart rate sensors. And so I put that link here. So all of these use just the heart rate information in order to generate these assessments. And so as long as you have an accurate heart rate monitor and you're confident in the value that comes out, the data that comes out, you can do this. I'll tell you one thing you also really need, though, to do this right, besides the accurate heart rate monitoring. I should have mentioned this to you earlier, but I'll mention it now, is you really need a confidence flag. You need a confidence indicator to know that heart rate data is correct. And, our benchmark sensor outputs a confidence indicator. So you can know whether or not you can really trust that data or not. So if ever you do find a heart rate monitor you want to use for this, you'll look at it with your eye and you'll go, oh my God, I totally see the pattern. But then when you want to autonomously do it, you run into trouble unless you have a confidence indicator. I'll show you that next. Here's some of our own data. Actually, this is my data. So I see that, unfortunately, the back image is dropped, but we did we collect a lot of heart rate data here at Valencell, and our partners do. And so this plot was a circadian rhythm analysis of me, and it was me wearing a wearable device for a few days and looking at my heart rate changes. And what this exploded view here is just off my sleeping stage. And what's interesting is you can see where I've had a good and bad sleep here. For example, my REM sleep is clearly identified by the 3 little peaks you see there, where I was going in and out of different stages from deep to REM sleep, where I was actually dreaming. And when I started to not sleep well, you see that pattern is lost. And so you'll see this. And now you look at this, and as a human, you go, oh my God, I totally see it here. But you got to remember now, a big thing about wearables is trying to make this autonomous, trying to make it to where a computer could look at this and pull this off. And that's non-trivial. for a computer to look at this and say, okay, I see the stages, I get it, and this is bad sleep. And so one of the things that you have to do is you have to perform some algorithms, and it also helps in some cases to implement some machine learning to use this data to differentiate between the stages and understand the difference between good and bad sleep. But you can really do this with a heart rate monitor if you have not garbage data coming out. So let's talk about stress. Now, probably the most mysterious of any of the different biometrics that are picked up by PPG or heart rate probably is stress. And the reason is because, first of all, the confusion people have about the definition of stress. And then also, and this is, by the way, this is not just people in general, this is people in the field. But also another thing is how do you use heart rate variability analysis to understand a change in stress versus something else? And I'll give you an example. If you look at RRI output from, say, a benchmark sensor, and you're trying to study someone over a period of time to understand whether or not they're stressed, well, their heart rate variability may get really low, which is typically not good. And how would you know that that's because they're suffering from a cardiovascular issue, maybe, or they've exercised too much, or they're stressed, psychosocially stressed? You know, maybe their girlfriend or boyfriend broke up with them, for example. How would you know that? And that's where the biggest challenge is in a stress assessment. And so one of the things that's becoming more popular now in the PPG world is to do stress analysis based off sensor fusion, but sensor fusion within the PPG sensor. So what you do is you look at not only the heart rate information and the RRI information, but you might look at information in the PPG wave itself. For example, what is the intensity of the PPG wave, and what's the area under the curve for the PPG wave, and apply that to speciate between different types of scenarios that cause your heart rate variability to change. So one of the papers I linked here for you is a paper by this researcher, Broschat. He's done a lot of work in stress and worry and how worry affects your cardiac health. But not only that, also how your valence affects your health. And valence is a term used in psychopsychology where when you have a positive view in a particular way, you have a positive valence. When you have a negative view, you have a negative valence. So it's your attitude. And he's done a lot of work on this. I put one paper here that I thought was really useful because it describes how you can use the heart rate and heart rate variability to assess whether or not someone is worrying or not. And he explains how to do this in this paper. But I would recommend you look at a number of Broschat's research, a number of his papers. You can go online and see he's been pretty prolific in writing about this topic. Now, you can do this HRV analysis to assess one's stress, but let me tell you what I found particularly interesting. One of our collaborators in this space is a company called FirstBeat. They're located in Finland, and they've been in this field a long time. And I got to say, the most interesting use of heart rate variability I've ever seen has been at a conference that they started this past year. I was there in April, and there was a presentation given by a girl named Erica Thyman, who is a professor in the United States, who has done a lot of research with the FirstBeat technology. And what she was able to show was how the FirstBeat technology, what it really tells you is you can take heart rate variability information, you can take RR interval and process it through FirstBeat's algorithms to get an indication of how well you are able, how ready you are to manage a stressful event. So this value tells you how capable you are as a person to manage a stressful event, and it really works. Some of the research that she did is she looked at how, in particular, she does a lot of work with folks who feel that they're very stressed and they're not able to perform in their jobs as well as they'd like. Maybe not perform well as students or perform well on a job. And she's done a lot of work to correlate alcohol consumption with a disruption in heart rate variability that is associated with your ability to be ready for a stressful event. And she's able to show how people on an individual basis how them reducing the alcohol intake has improved their heart rate variability and their ability to handle stressful events. It's actually quite impressive. Unfortunately, I can't find any papers by Erica on this. She's given presentations on this. Let me know if you want her name. I'll pass that along to you, and you can check out with her and see if you can get her presentation. I have a copy of it. I just don't know if I'm allowed to share it beyond what she's presented, but it's very interesting. It's very powerful, I'll say. You can also use HRV from the RI outputs to understand the correlation between stressors versus stress. So what is the cause of your stress versus the outcome? If you read that paper I have on worry-related stress, this link, they go into detail about how to do this, how to use a diary for stressors in order to help you understand, okay, is the person really stressed here, and is it caused by the stressor? Now, another thing, like I mentioned earlier to you, is you can look at the PPG amplitude, and you can understand, and by looking at the PPG amplitude, use that as an input to understand stress. So I think I have some data here. Yeah, here we go. This is some data from one of our benchmark sensors, and in this particular case, this participant was exposed to 3 different stressors. And then we looked at the PPG output. In this particular case, we said, let's just look at the PPG amplitude only, which is related to the blood flow dynamics, the blood flow change. So you could kind of look at this, to oversimplify it, you could kind of look at this plot as a proxy for blood flow. And so when you look at this blood flow intensity versus time, you'll notice that when, the stressful events in the body's response to them are pretty clear. Now, this was using just PPG amplitude, and I wouldn't recommend you use only PPG amplitude to look at a stressful event. But what I recommend is that you combine heart rate variability with the PPG amplitude as a way for you to gauge whether or not someone is really reacting dynamically to a stressful event. That extra layer of that kind of sensor fusion within the PPG signal itself can be extremely useful in helping you speciate between these different origins of what this heart rate variability is telling you. And not only that, not only the PPG amplitude, but you can also look at the area under the curve, as was a lot of explanation of that is in the Karmakar paper that I referenced to you earlier on how to do that. And he goes into a lot of detail about that. So now that concludes my presentation, and I'm going to open it for Q&A. But I'd just like to summarize by saying I went over just a few things you can do with a heart rate-based PPG sensor that we already provide. And as long as you have an accurate heart rate monitor, have accurate activity context, and you also have a confidence indicator, you can do all these things. You can implement all these things. Some of our partners have implemented some of these already, particularly VO2 max. Also, some of our partners have implemented heart rate recovery and training effect. But there's others that still are pretty untouched, and there's not enough implementation of the technology for stress analysis, and not enough implementation of the technology for sleep analysis as well, and how the sleep analysis relates to health. So with that said, I'm going to go ahead and open it up and see if y'all have any questions for me, which I'm happy to address. Thanks for your time. So one of the questions that was asked here is, how do they get the links? The webinar doesn't allow to follow the links. So what we'll do is our marketing manager Casey Webb will provide y'all with a PDF of this PowerPoint that you can just simply click on the underlined areas, and it'll have the links built into the PDF file. And I do highly recommend those references. Some of those papers in particular are really good. And if you have any questions about implementation, we're happy to be collegial and share with you what we can. At Valencell, what's interesting is the goal when I started this company, it wasn't focused on developing the use cases. It was focused on developing the core technology that you can use to implement those use cases. But what we found is that we have to help people understand how to implement these use cases in order to get them out there. And so we have gotten more involved in helping our partners use biometrics in compelling ways that help them to launch really compelling products. So one of the questions that was also asked is, could I elaborate more on hydration? Now, hydration is a tricky one to explain, and the reason why, remember how I talked earlier about how stress, one of the problems with stress analysis is what is the definition of stress? And that's one of the challenges with hydration. When people talk about hydration, that there is many different types of hydration. For example, there's blood osmolality, which is, if you kind of look at it as your hemodynamic aspect of hydration, your blood hydration, if you rather that. Another one is urine analysis, where basically you look at how much water is in your pee, and that doesn't always correlate with your blood osmolality. Another one that we hear a lot of commonly is skin hydration. So that's the moisture content of your skin. And all three of those, and by the way, there's other classifications of hydration. Those are just three that come to mind immediately right now that are important, and they don't necessarily correlate with each other. And so one of the questions is, what do you mean by hydration? And I'll tell you, what I'll do is I'll give you an example of how one of our partners used it. And they were using it to get an indication about whether or not somebody might need to drink water. And the way that they were looking at it was, you see, if you say you look at an output of a benchmark sensor, one of our sensors, we output the heart rate in real time. We also output the PPG amplitude in real time. And if you look at the heart rate, the heart rate is in beats per second. And if you look at the PPG amplitude, it's in terms of volume per beat. So you multiply those together and you get volume per second, and that's indicative of your perfusion. And so you can tell by that multiplied output what the blood flow dynamics are. And what they were finding is that when the perfusion started to jump up dramatically during a run, that was an indication that people needed to drink water. At least that was in their preliminary estimations. And so those types of studies are going on right there. That's an example. There are other methodologies you can use in order to estimate hydration in different types of hydration, but that's just one example that I can discuss, that I'm free to discuss about, at least at that level. So, folks, I do have time for a few more questions, and I guess I'll wait a minute more, and if there aren't any more questions, I'll let you get back on with your day. Well, I got a technical question here about power management in our devices. And I guess, please feel free to ask the question. If I can answer it, I'm happy to.
The conference has been muted.
So the question is about how often we monitor the heart rate during 24 hours. We provide some suggestions to our partners, but different partners pick different types of ways to do this. So we recommend that people, in say a 24-hour session, that people look at the heart rate no less than 6 times within that hour. Typically what this means is you turn on the heart rate monitor, you do a measurement for a few seconds, and then you turn it off. And some folks like to do more than that, some not. But you can really reduce the power substantially if you do that. And it depends on the use case, which you want to implement. If you're trying to get an understanding of someone's, say, circadian rhythm and the heart rate throughout the day, that is plenty enough. If you're trying to do a stress analysis of somebody, that's a different story. Because when you do a stress analysis of someone, you really want to turn the sensor on and have it measured for 5 minutes solid to collect enough statistics on the RR intervals in order to get you something useful. So in that particular case, if you don't want to burn the battery down too much, we certainly wouldn't recommend that you do that more than a few times an hour. So for example, like maybe even just 2 times an hour in order to do that analysis. Yeah, one of the questions that was asked here is how would you recommend doing this in a hearing aid? And I tell you, one of the things that you can do for hearing aids is it turns out that you don't need nearly as much power in the earbud as you need for the wrist. And the reason is because you don't need as many wavelengths, or rather, you don't need as many optical emitters as you do with the ear as for the wrist. So the wrist power is much higher than what you use for an ear to get the same level of performance. And the reason is because in the ear, the blood flow dynamics are not nearly as complicated. And so you get the benefit right away of less power consumption in the ear by virtue of simply being in the ear. And also benefit from the fact that the intensity of that one LED does not need to be very high, because the perfusion is higher in the ear than it is in the wrist, and the motion artifacts are less. So integrating into a hearing aid, I will say we do have partners that are integrating our technology into hearing aids. And there are a number of techniques you can use to reduce, clever techniques you can use to reduce the power consumption in a hearing aid for heart rate monitoring, depending on the use case. So for example, if you want to determine whether or not someone has atrial fib, you sure as hell don't need to be on 24/7. That's a complete waste. You see, with doctors, what they'll typically do to determine if you have atrial fib is they'll perhaps give you a Holter monitor and ask you to wear it for quite a number of days. And the reality is that people never wear it that long, and so they're lucky to get 1 or 2 days of information, and they have to look at all that data and then see if the atrial fib pops out. However, in a hearing aid, what's interesting is by virtue of that modality of people using you on a daily basis, you don't need to measure them continuously like you would for a Holter monitor in order to pick up the atrial fib information, because the compliance is so much higher. And so you really, one of the 2 ways to really reduce the power in your wearable device, well, there's 3 ways, I guess, in particular. One is where your sensor is located. The ear is a really great place for that. 2 is the way you do your processing and the optical coupling to the part of the body to improve the power management. But then the 3rd thing is the use case itself. How do you manage your power consistently with the particular use case you're going for. And so all those things need to be factored in.
The conference has been unmuted.
All right, y'all, any other questions before I let you get back to your days? All right, then. Well, look, folks, thanks a lot for your time, and we are going to be following up with you with that PDF for the links that y'all want, and we are happy to address any questions y'all have. Y'all have a good rest of the day.